where dual fluorescence is very important is because that compounds exhibiting dual fluorescence, they have applications like DNA detectors, white OLEDs, fluorescence probes, pH indicators, and many more. But how we can bring the green fluorescence protein to this dual fluorescence? So this is the GFP chromophore or green fluorescence protein chromophore called PHBDI. The structure of PHBDI is here, and it has been shown in earlier studies that in many cases this compound exhibits dual fluorescence. Of course, not always, but in some cases it also shows single emission, and some cases it also shows non-fluorescence properties. So that's why the main crux, that's why we are using the GFP or green fluorescent protein. Now, if we talk about a little bit about history about the green fluorescent protein, so it is extracted from this Echuria pictoria. So it emits actually green color when it exposed to light. And if I talk about the structure, it is a 11-stranded beta barrel structure with nearly perfect cylinder kind of structure, which has 24 angstrom in diameter and 42 angstrom in height. So if I see that which chromophore or which part of the amino acid sequence gives the structure this color, is basically this three sequence like serine, tyrosine, and glycine. And you can see that this is the structure that I was talking about. Okay, so when I talk about the green fluorescence protein, so it has many forms like cationic forms, anionic forms, neutral forms. The wild type of green fluorescence protein actually, they absorbs in two wavelengths. One is 398, which is a major absorption, and there is 475, which is a minor absorption. So if we consider a major absorption, that is at 398 nanometer, and which corresponds to the neutral GFP chromophore, and it undergoes actually at that frequency a repeat excited state proton transfer. And once we do these excitations, it yields a green fluorescence protein at 508 nanometer with maximum fluorescence yield of 18%. So it's very, very interesting to see that this kind of chromophore can yield this much of fluorescence called quantum yield. Now, so this is the structure of the proton transfer chain in this normal PTHBDI. Now, analogous to this one, there are a lot of synthesis being done. So one of the compound or one of the analog of GFP is called PTSABDI, which is the structure of this one. And for this compound also, as we can see shortly, that this compound actually also possibility of show the excited state proton transfer, because it can mimic the what natural green fluorescent protein chromophore can do. Okay, so in earlier studies it was shown that the effect of solvent on the photophysical phenomena of PTS-ABDI analog, but they did not show what is the mechanism behind that why it is showing the dual fluorescence. So it is our objective that why this kind of GFP analog can show the dual fluorescence, as well as we like to show what is the mechanistic pathway. So in order to do that, so what we have considered in this investigation, we have considered the normal GFP chromophore as well as the two GFP chromophore analog like PTS-ABDI and PTS-ABDI after proton transfer, and these are the chromophore complex. So to begin with, we calculated the absorption and emission spectrum, and as you can see that the results, the experimental results and our computed results are very good in agreement. And you can see that if I consider the acetonitrile case, solvent case, so our values are and experimental values are very close. Even for DMSO, its values are matching. So however, in order to test the validity of our approach, so what we did, we checked the same thing for the naturally occurring PHBDI. So what we have found that in that case, that results are very, very encouraging. especially if I go to this ethanol case, where both experimental absorption and emission values are available, you can see results are in very good agreement with the experimental data. Then we decide that, okay, so since we are talking about proton transfer, that how many solvent molecules are required in this kind of study. So what we have seen, that we have tested 3, 4 and 5 solvent molecules. In this study we have considered water and methanol. If we consider the water case, we have seen that for a 3 solvent model case, the energy barrier is lowest among the other 2. So we can say that for this kind of system, maybe 3 proton transfer or 3 model solvent molecules may be a right one. Similarly, we have seen for your methanol also using the similar 3 solvent molecules. So what we did, so from here on we have considered the 3 proton or 3 solvent model for further study. Then what we have decided, that since we are talking about the proton transfer or intermolecular proton transfer, so we can see that what is the structural changes happens during this transfer. So if I consider the 2 cases, of course there are many cases are there, you can see that if I consider the N1H1 bond of the during the proton transfer, you can see there are some marginal increment, okay, and that increment is becoming some more pronounced if you go to the excited state. But if you go to the hydrogen bond between H1 and O1, you can see that these values are decreases when you go to the excited state. That means in excited state, the hydrogen bondings are basically strengthened. So that can be also seen if we consider the chromophore part. In the previous case, we talked about the solvent part. In this case, we are talking about the chromophore part. Specifically, if I say C4, C7 bond, then C7, C8, and C1, CN1. So there are other cases also you can see, there are some changes. So here also you can see some changes. Then we say that, okay, in order to further test the validity, what we have done, so we have calculated the IR spectra of both water complex as well as the methanol complex. And what we have seen, that in the excited state, so there is a red shift happens if you consider specifically this N1H1 and O3H4 bond. So this means again, since there is a red shift, we can think of like that intermolecular hydrogen bondings are again strengthened during this proton transfer process in the excited state. That can be seen in the for methanol case also. Then after that, what we have done, so in order to see the electron localization, as you can see, if I see from the frontier molecular orbitals, you can see that this electron density delocalized over this chromophore ring. So electron density is not going to this solvent system. Since we are talking about a 3 model, 3 proton, 3 solvent model, so you can see that it is delocalized over here. So we can see that there is a possibility, or there is a pi to pi star electronic transition happens, and there is no electron density can be found in the adjacent solvent molecules. Similar things can be seen in this methanol case also. And if we take the difference between HOMO and LUMO, these values are 0.131 and 0.130 EV respectively. So what does it mean? That these values are small in comparison to if you talk about in the ground state. So this means that there is again a more likelihood that there is a proton transfer process may be possible in the excited state. Then what we have done, we have calculated the potential energy curve of this excited state intermolecular proton transfer process. So as you can see, so here we have calculated 2 properties. One is delta V. So delta V is the proton transfer energy barrier. That means I am talking about difference between this and this, this and this. And delta E is the your relative reaction energy, means difference between reactant minima and then product minima. So what you can see that the barrier from ground state to excited state, it basically decreases from 18.8 kcal to 12.7 kcal for water complex, and for methanol complex it is decreasing from 18.9 to 9.9. So that means the barrier is decreasing, means there is a possibility, but again let me tell you that this is an endothermic reaction. So that can be seen here also. So from this process, what we can propose a mechanism for ESIPT is that let's say we start with this neutral form which is there in the ground state, and after absorption of the light it goes to the undissociated excited state. From there may be two possibilities. Either it can emit, it will come down, or it can have excited state intermolecular proton transfer. If it is so, it will become a dissociated excited state, and from there again emission may happen. It can be radiative or it can be non-radiative, and finally it can come back to the dissociative ground state. And again there is a possibility that there is a reverse proton transfer can be possible. So I'll finish. So this is the RDC scattered plot and NCI isosurvey plots, which shows that there are hydrogen bonding involved. Due to the paucity of the time, I will not go. I will focus on this, the main thing about this excited state dynamic simulation. So what we have done, that we have tried to see that initially hydrogen, this is the N1H1, and we can see that there is a proton transfer. H1 will move to O1, H2 will move to O2, then H3 will move to O4, and H4 will move to N2. So there is a 4 proton transfer happens, and you can see that this is the timeline. So for the first proton it is 64 around, for second proton it is 170, third proton it is 139, and fourth proton it is 183. So it means it is happening like a wire kind of things from one proton to the final protons. And another thing is that if I look into the energy difference between the ground and excited state, what is happening? The values are fluctuating between 2 electron volts, means there is no conical intersections between S1 and S0 state. So, okay, so these are the proton transfer process. So if I see, let me show you the process. So you can see that this is done in different software. So you can first proton transfer, second, and from second to third, and third to fourth. So you can see that those whatever the 4 proton transfer process that we are talking about, that can be seen from here. Okay, so there is also non-proton transfer process are also available, because as I say, that reaction is endothermic. So most of the trajectories, we have done actually 100 trajectories analysis, and most of the trajectories shows non-proton transfer process. So this is for methanol, and again here also non-proton transfer process are there. So if I summarize the result from our study, that out of 100 trajectories, 23% for proton transfer probability is there for water complex, and 28% there is for methanol complex. So finally, in summary, what we can say that this GFP analog, that is PTS-ABDI, it exhibits unusual dual emissive characteristics in polar solvents. Then static calculation demonstrated that PTS-ABDI analog undergoes structural rearrangement in the excited state, and thereby strengthening the intermolecular hydrogen bonds. And this intermolecular hydrogen bond induces ultra-fast excited state intermolecular proton transfer process. And when we talk about PEC, proton transfer process is more favorable in S1 state, owing to the comparatively low proton transfer energy barrier, and it is endothermic reactions. And excited state investigation revealed that ESIPT reactions are ultra-fast, occurring in stepwise manner. So what is the take-home message from here, from our study? We can say that since we have done both static calculation and dynamic calculation. So this, with the help of these two calculation, what we can say, we can design, and of course pave a way for the experimentalists to synthesize GFP chromophores which can improve photophysical properties. So with this, I'd like to thank my PhD student Bittu. So for more details, you may visit our poster of course IIT Guwahati for infrastructure facility, and Parameshan supercomputing facility. So I'd like to dedicate this talk to my teachers. So stay safe and thank you. Thanks for your questions.